Now here, let's tie all of what we learned in terms of antennas, directivity, effective area, and take a look at what that means for transmitting and receiving an electromagnetic wave signal. And the main formula that describes that is the Friis transmission formula. And the manipulation of this formula and the amount of power that you have or need to have, this is also often referred to as looking at the link budget of the system. So this is the main concept that we're going to introduce here. So let's take a look at this step by step. So we're going to look at a basic communication scenario where on one hand you have a really big antenna transmitting tower. It sits really high off the ground, and it radiates a certain power with a certain amount of directivity. Right. So this is the transmitting side. It's broadcasting the sporting, the athletic event of your preference. So we have a football match that's being transferred through the radio waves. Here you are. Grateful that it's on broadcast, because at this stage you're not paying for cable, so you have your receive antenna here that you want to capture this signal with. Right? So here's your transmit, here's your receive, and now let's see how far we can get using the information that we have, using the knowledge that we have so far. So over here, it's going to start radiating its signal in the form of a plane wave, right? So as it goes in this particular direction, there's going to be a certain amount of power that it transmits. And then if we know the direction between your source and your receiver, your transmitter and your receiver, you also have your directivity that's evaluated at that particular theta and phi, right? So this is the average power that you have. The directivity tells you how much of a boost or reduction penalty you have, depending on, that's based on the direction of your receiver relative to the antenna, right? Now next up, let's say that you are sitting a distance r from the transmitter. So now over here, this is going to diffuse as a function of the surface area of the sphere of a radius r, right? So as r increases, this amount of power density is going to decrease based on the surface area of this sphere. So over here, the power that we have is going to be P1 D1, but now it's going to be reduced by the surface area of a sphere of radius r, which is what? That's right, 4 pi r squared, right? And now over here on the receive side, you're going to have, so this gives you the power density, right? This is in watts. This is unitless, so this is just a boost, right? And then over here, this is 1 over meter squared. So on the receive side, you now have this power density, which is watts per meter squared. Now, how do you translate that into actual receive power? That's right. So to convert that into watts, you multiply it by the effective area that the antenna has to capture this radio wave, right? So you multiply it by the effective area. So this would be P1 D1, and then you have a penalty of 4 pi r squared, and then you multiply it by the effective area. And then that will tell you how much power is received, right? So to put it all together, the power received is going to be equal to P1 times D1 divided by 4 pi r squared, and then multiplied by the effective area, right? And the effective area, if we go back to that discussion, the effective area is related to the directivity of the receive antenna through the expression lambda squared over 4 pi d2, right? So let's plug that in here. Lambda squared over 4 pi d2. And so this, we can also do some rearranging. put this lambda squared. You have two 4 pi's, you have an r squared. That all looks nice. So now you can also simplify and say that your received power is going to be equal to P1 d1 d2 times lambda over 4 pi r squared. Oops. Lambda over 4 pi r quantity squared, which, going back, was P1, let me just write this equation here so that we have it all together, which is P1 d1 1 over 4 pi r squared, and then the effective area of the receive antenna. So this is the Friis transmission formula. And the main thing that I want you to observe is that, so if you walk through this process, you can kind of see the logic, right? You start with your transmitting power in watts, you get a boost or a penalty, depending on how favorable your direction of travel between transmit and receive is relative to the antenna field pattern. And then you start, as you get further and further away, it diffuses as a function of 4 pi r squared. And then you multiply it by the effective area on the receive end to figure out how much power you end up receiving. And then with some manipulation, because effective area is lambda squared over 4 pi d2, you can write this as an expression of related to P1, the product of the directivities of the transmit and receive antenna, times a factor of lambda over 4 pi r quantity squared. And so looking at this, there are a few key conclusions that you can see. Right. So first of all, this is called the link budget because you can see if you need a particular receive power, you can make your trade-offs. Right. If you have a particular antenna and a particular amount of transmit power, then you can figure out and if your receive antenna is also set, you can use this to figure out how much power, how close you need to be in order to receive enough power such that the system actually works. So one immediate application where this comes in is that by looking at this equation, you can talk about why high frequency communication, like the rise of 5G that everybody's working towards, or the use of millimeter waves to do communication, is so challenging, right? In addition to just the fact that these higher frequency signals, especially in the millimeter wave regime, tend to have higher atmospheric absorption and less ability to penetrate. Remember, skin depth. The concept of skin depth is related to the wavelength, and so as the wavelengths get shorter, it's harder to penetrate barriers. But secondarily, from a transmission formula point of view, you can see that as the frequency increases, lambda is going to decrease, right? And so if lambda decreases, you take more of a penalty here. Remember, you see that a lot of this is related to the relationship of lambda and r. So you can think of it as the farther away the source and the receiver, the transmitter and the receiver are in units of wavelength, the more diffuse the power is going to be, right? So as you increase in frequency, your transmitter and your receiver is now effectively farther and farther away. So you take a much larger penalty due to this diffusion that occurs as you propagate outwards, right? Because this 4 pi r diffusion is actually also, through the effective area formula, is also kind of normalized by wavelength. So as you go further and further away, you're looking at it in units of wavelength, you're going to suffer greater and greater losses due to power diffusion. So where else can you make up for that? Well, your power, if anything, your receive and your transmit power is now even more constrained because of the way physics works. A lot of our tricks that we have for generating high power sources just don't quite work as well, especially from a solid state standpoint at these higher frequencies. So the only trick you have left is the directivity. And so what that means is that to make up for these extra losses that you get by increasing the frequency, which gives you more bandwidth, lets you upload and download videos faster and all that good stuff. But separately, in order for your link budget to work, you really need to boost the directivity of your transmit and receive antennas. And so what that means is that instead of a light bulb where you're just you can transfer waves in every direction and get away with it, now Instead, you have something that's more like a laser beam, right? A pencil beam that you need to point in order to have the gain needed to make up. And separately, on the receive side, here's this person with their fancy 5G phone. Their 5G phone is also going to have a high directivity antenna for this link budget to work, right? And then to make things even worse, if this person is sitting in a car and traveling at 100 kilometers an hour, now all of a sudden you're really in trouble, because these beams now have to be steered accurately in order to maintain the link. And so that's why, while high frequency communication has a lot of possibilities, this is one of the key barriers and challenges that smart people are working to tackle. And as your phone gets these higher data rates and we start operating in these higher frequencies, we can, through this discussion here, have a greater appreciation for what exactly they really had to overcome to make these systems a reality.